the overall data. So the first way to sample from a particular distribution is rejection sampling. And here we assume that computing P of Z or P of X is easy. So what that means is that, let's say I have a distribution, right? And let's say the distribution is some complicated distribution that given any point Z, so let's say this is Z1 and this is Z2. Okay, so if I take a point Z, let's change the color. If I take a point Z, then I can compute P of Z, right? But that doesn't guarantee that I can generate samples from P of Z. Generating samples requires, so for example here, if I want to generate samples, I may want to use a separate distribution. I can easily generate samples from an axis aligned Gaussian based on the factorized distribution. So I can have some Q of Z1 and some Q of Z2. So these are proposal distribution. This is called a proposal distribution. Okay, and let's say this can be factorized, and it can be factorized into standard forms such as Gaussian distributions. So I can generate from one-dimensional Gaussian P of Z1, sorry, Q of Z1, and another one-dimensional Gaussian Q of Z2, and let's say I can multiply the two to get Q of Z. Now, using Q of Z, how will I generate samples from P of Z? So, and P of Z, mind you, is a complicated distribution for which I cannot easily generate samples, but I can compute, given a Z value, what is P of Z. So let's say this, so basically in rejection sampling, what we'll do, we will first generate a sample from Q of Z, okay, and then we will accept it with probability P of Z divided by K of Q of Z, K times Q of Z. So what is K? K is a constant such that K of Q of Z is greater than or equal to P of Z for all Z. So if that is the case, I have to find a particular K where it is, Q of Z will be greater than or equal to all P of Z. So now think of it this way. Now if I draw this in one dimension, right? So you have some complicated distribution, and we have, so this complicated distribution is P of Z. Okay, so this is Z, and the other thing is the other axis is the probability, and I take Q of Z, which is a simple distribution, and I increase its height to the extent by multiplying with K, so that it is always above P of Z. So this is Q of Z, K Q of Z. Now, once I sample from P of Z, I have this much probability of sampling it, or something proportional to this. But I will accept it only when in this proportion, which is the proportion of P of Z, and I will reject those that are above that. So ultimately that means I will be sampling from P of Z. The disadvantage of this is that there are, wherever this ratio is small, right, P of Z is much smaller than KQ of Z, then I will reject a lot of samples in that region, and I will be generating a lot of, I'll be wasting samples in those regions. Plus the other disadvantage is that I have to find a good value for K. Otherwise this scheme will not work. On the other hand, there is another strategy where we do not reject. There is a second strategy where we do not reject any sample. We accept all samples except that we assign them weights. So where this is useful is, let's say we are trying to integrate, we are trying to find the expected value of f of z, which is f of z times p of z. Okay. Instead of that, what we will do is we will sample z from qz, which is easy to sample from, right? So we will have sum of f of z, okay, but we will also have w of z, some weight w of z, okay, and where z is sampled from not p of z, because that is difficult, it is sampled from q of z. So this symbol means z is sampled from q of z. Okay, so it will help us do this integration, and this weight is now the ratio, so that we know that from Monte Carlo, if it was sampled from z, then basically this would have been, if we didn't have the weight, this would have been integration over q of z. Now we are replacing that q of z by actually taking the ratio of p of z to q of z, so that it actually becomes integration over p of z. So this is the importance weight, importance of a sample, importance of sample z. Okay, so that's why it is called importance sampling. So there is no rejection, no samples rejected. It's another matter that it suffers from the same problem, that we may have a lot of very small weights because the ratio of p of z and q of z are different. So in both these cases, in rejection sampling and importance sampling, what is to be kept in mind is that q of z should be a good replica of p of z. Otherwise it will either reject a lot of samples or it will drive a lot of sample weights to zero. So that should not happen. For both of these cases, if we don't find a good replica of p of z and q of z, then we will get inefficient sampling. So if we don't find a good q of z, there are other ways of sampling from p of z by constructing something called a Markov chain. So what we saw before this, that all the samples that were sampled, all the z samples that were generated from q of z, they were independent of each other. They were IID, independently and identically distributed. Whereas in Markov chain Monte Carlo, the sample that will be generated will be based on the previous sample. It will have a conditional distribution over the previous sample. So so basically, when you generate a sample, the next sample will be likely to be close to it. And if we want to sample from a distant part of the space, then only when the chain actually goes in steps and reaches that part, only then we'll be able to generate the sample from that other part of the state. So these will all be, so there will be a Markov chain, and the chain will be slowly moving in the space. And if the chain is long enough, then if we take all the samples and we shuffle them, they will look like as if they are IID. But if we just look at the sequence in which they are generated, they will not be IID. So basically what we are trying to do is the following. So let's say we have a complex distribution and it is spread out like this. So these are the contours of equal probability in Z1 and Z2 space. Okay. So what we are trying to do is trying to generate a random sample, and then we are trying to generate other samples close to it, okay, and slowly generate a lot of samples, so all these are in a sequence, so you will see a line through them, and we are slowly trying to generate a lot of samples so that it explores everything in the large space. So when we generate each of these samples, these contours of conditional distributions will be small. Okay, so we are only exploring a small neighborhood, and this could be an isotropic Gaussian, for example. We are taking a small step in the nearby neighborhood, but the probability of accepting that step would be based on the relative distribution of the initial point versus the next point. Okay, so that's what we are looking at, and overall, when we take, let's say, 1,000,000 samples, then hopefully we have explored everything in the original distribution P of Z. Right? So again, P of Z is easy to compute, but it is not easy to sample from. That is the assumption. So here, the other advantage is that now this Q of Z need not be a good replica of P of Z. It is only a good replica of the neighborhood in some sense, or it doesn't even need to be like that. It just needs to be exploratory enough in the neighborhood. So so here we will iterate over the number of samples T. Okay, so that will form a chain. T is equal to 1, T is equal to 2, so T is equal to 1, 2, etc. Then we'll reach T and then T plus 1. Okay, so we are generating a lot of samples. So when we iterate over T, whatever was the last sample in the chain, right? So your chain is like this. So this is the chain, and so let's say this is T and the next one is T plus 1. Okay. So what we are going to do is we are going to generate a sample from QZ given ZT. So whatever is T, we will take an isotropic Gaussian and we will sample from that distribution. We'll get some Z. Now we will either accept this Z or we will reject this Z with some probability. The probability of acceptance is a minimum between 1, right, because it cannot be greater than 1, and a ratio of two things. The ratio is that of P of Z divided by P of ZT, and the inverse of P of ZT given Z and Q of ZT given Z and Q of Z given ZT. Okay. So basically what this means is that so actually we wouldn't need this. We wouldn't have needed these two terms if this was symmetric. If these are symmetric, then we wouldn't have needed those terms. These would have cancelled out. Essentially what we are saying is the following, that from a low density region, relatively low density region, if the exploration step, right, the generated sample, so if you have ZT, and so this is ZT, and let's say this is Z. So if the relative density of Z is greater than that of ZT, then surely accept ZT, then take that step, otherwise stay at ZT. Okay, so either stay at Z, either go to Z or stay at ZT. So we surely accept if basically P of Z is going to be P of Z is going to be greater than P of ZT, and if it is less, then we might reject that sample. Okay, so we will reject it with the probability P of Z divided by P of ZT. The other thing, these two terms are only to account for the fact if the jumps were not symmetric, so usually they are not even used. So essentially, if we use the terms, it is called Metropolis algorithm, and if we use a non-symmetric Markov chain, then it is Metropolis-Hastings algorithm. Okay, so in Metropolis algorithm, we will just have min of 1 comma P of Z divided by P of ZT. So where you are coming from, so you are more likely to go to places where the probability is higher. That's all it means. Right. So imagine if you had a chain that was way out somewhere in the low probability region. It started there because our first sample was randomly generated. So here it will spend a lot of time, the chain will meander in the low probability region before it gets here and starts to explore the high probability region. So usually the first several samples of the chains are rejected. That's called the burn-in period. After that, we can accept the chain, and we can also have multiple chains running so that so let's say if it is a multimodal distribution and the other mode is very far away. If we explore only this region, but this chain never escapes to the other mode, that there's a probability of that. So we actually can have multiple chains, and then we can take all the chains, the samples generated by all the chains, shuffle the samples, and we have a good IIDs kind of looking sample from the particular distribution. The last topic that we will talk about in generating samples is Gibbs sampling. Here this works well when we have conditional distributions, that is, we are able to generate the ith dimension given all but the ith dimension. So this notation \i means all the dimensions of z except for the ith dimension. So if we have, so for example, let's say we have three-dimensional, okay, z1, z2 and z3. So if we can generate samples from P of z1 given z2, z3, and we can generate samples from P of z2 given z1, z3, and we can generate samples from P of z3 given z1 and z2. Okay. If we can do that, if we have these three conditional distributions, then we can use Gibbs sampling. So what we would do is that we would iterate over the number of samples. We would iterate over dimensions. This is not samples, this is dimensions. And we would generate the ith dimension of the t plus 1th iteration, okay, by using the conditional distribution of the ith sample with all ith dimension given all but the ith dimension. And this itself can be done, let's say, using Metropolis, like a rejection sampling or some of the other sampling methods that we have talked about before. So this gives you some idea about how samples can be generated, how distributions can be estimated using a parametric and a non-parametric form, and how we can use it for finding expected values of certain functions in machine learning. Thank you.